Ta-da! We finally have a whiteboard, which means that I can move on to finally talking about interview practice. Okay, so today we will concentrate on one part of interviews that often comes up, which is graph plotting. You might say that with tools like Wolfram Alpha, it's a useless skill, but I disagree. Same goes to fast mental arithmetic and calculator. Sometimes you just gotta think on the spot, and interviews is actually one of those times, so let's practice.
I just want to tell people that graph plotting will never be a whole interview. It might be just one or two graphs, but you do really need to know how to make them, so it's a useful skill.
Let's start with reminding ourselves about some definitions which the interviewer might ask as a warm-up question. What is an even and odd functions? An even function is the one that satisfies this equation. The minus sign is kind of swallowed by the function as if it was never there. So we get a function symmetric in y-axis. And the odd function kind of spits out the minus sign. So you get this equation. Now, the interviewer will never jump to a very hard question, and if they do, they might want to see your reasoning and intermediate steps. The easiest example I can come up with is this one, minus 2 e to the minus x plus 5. It might look kind of scary, like what are all these minuses, but let's start with something that you do know, like e to the x. For x equals 0, we will have e to the x is 1, then for big x's we will tend to infinity, and for small 2, 0. So we put a dashed line there with a crossing at 0, 1. What about minus e to the x? Well, that would be a reflection in x-axis, so all the values that we had for y will be negated. So 1 will become minus 1, and we will still have the tendency to 0, but then for big axis we will tend to minus infinity. So that was a reflection in x-axis, and now for minus e to the minus x we need to reflect in y-axis, and the graph will look like this. The first transformation that we need to apply is multiplying by 2, which means that all the negative values will become even more negative. So the intersection will go from minus 1 to minus 2, and all the negative values will kind of go even lower. The last thing we do is a translation by 5, which means that we move the whole graph by 5 units up. The intersection with y-axis will go from minus 2 to 3, and then the asymptote will go from 0 to 5. Now you noticed I've omitted the intersection with x-axis, so if the interviewer asks you that, you just go easy. You write down the equation for y is equal to 0, then you make e to the minus x be on its own so that you can take a log. You take natural logarithm of both sides, and then you invert the x, which means that you invert the inside of the logarithm. And there you have it, the first solved plot. Let's now get to the harder example. I want to teach you how to approach these sort of problems in general, because with the previous example, you could just do it in 4 steps of 2 reflections, 1 stretch and 1 translation. And now you're looking at this scary thing and not knowing where to start. Here is the list of points I go through to analyze a function. So I start with domain and range, i.e. what kind of values can x and y variables take. Sometimes if y is equal, for example, 1 over x, then clearly x cannot be 0. But it's certainly normal, of course, to have domain and range as a set of all the real numbers or, for example, all the rational numbers. The next thing you can do is to look at crossings with y and x axis, i.e. if you set x to 0, what will y be? And the opposite, if you set y to 0, what are x's, i.e. what are the roots of this equation? The next two are also very quick checks. For example, is y a periodic function? Is y of x the same as y of x plus some period? And also, is y an odd or even function? Based on the definitions that we discussed in the beginning of this video. We can also look at what happens in the limit. Where does the function tend as x tends to plus infinity or minus infinity? Another interesting thing is when the first derivative is 0, this will give us the points where the function behaves as increasing or decreasing, and when the second derivative is 0, that is concave or convex behavior. Now let's apply this algorithm to this function. So both domain and range would be real numbers. There doesn't seem to be any restrictions. 0 crossings are shown. The function is not periodic. I'll leave it up to you to substitute minus x, but after a quick check we can see that the function is neither even nor odd. Now let's look what happens when x is super big. We put it to the 5th power, but then we subtract x cubed. Still overall x5 grows faster than cube, so we go up. Same for minus side, but this time all the x's will be super big and negative, so we're going down. Solving the equation where the first derivative is equal to 0, we get 3 roots. One is 0, which will be special because it's squared, and then plus minus 1 over 2. I will omit the details for the second derivative, but you can trust me on that we have these values, 0 and plus minus a half. When putting them onto an x-axis, don't mess it up because 1 over root 2 is actually bigger than a half. There's a nice way of looking at stationary points that we were taught in Russia that I won't go into now, but basically pluses mean the function will be increasing, minus is decreasing. Similar thing with the second derivative, where the points kind of change from convex to concave, where plus is a smile. Now we know that the function will be rising at the start and then rising at the end. And in the middle it should be falling with the change in curvature at 0. So it should look something like this, and then we kind of try to align it and it doesn't fit, but it's okay to fix it. The interviewers just want to see you think. Then we check the curvature and everything seems to be okay. It kind of looks weird, but that's the right way, and we're done. Okay, one more function and it's the last one, I promise. This one is pretty cool and it kind of shows that you can do all those 10 points without really following them, just kind of keeping them all in your head and at least thinking about them once. So we have cos squared over x. Looks scary, but it's not. Let's start by drawing the axis. That's how I always start. It kind of makes me think that I am already halfway there. Okay, so as you can see, I'm kind of trying to break down the problem into smaller problems. Do I know how to draw cos squared? No. Can I try at least to draw cos? Yes, of course I can. That's something that every A-level student should be able to do. So I know that it's definitely in between 1 and minus 1. I also know it's even, so it will be symmetric around y-axis. And then its roots are pi over 2 and 3 pi over 2. And then starting from 2 pi, everything will repeat again. Okay, so how do we go from cos back to cos squared? Well, what we know is there will be no negative values whatsoever because it's cos squared. 1 squared will be 1, and then 0 squared will be 0, so those points will stay. When anything between 0 and 1 gets squared, it becomes smaller, so cos squared line will actually be below cos line. Then we have another 0 at 3 pi over 2. At pi we had minus 1 squared will be 1, so we kind of flip it. Then all the zeros on the negative side will kind of follow the same pattern. Now remember that cos needs to be smooth. It can't have any abrupt changes because its derivative has nice zeros. So we will have all those stationary points and we will connect them nicely, and there we have our cos squared function. We're almost there, we just need to divide by x. But what does it mean for our function? Well, cos is even, so we had a symmetry around y-axis, but when we are dividing by x, it will actually make the function odd. For negative x values, we will have negative y values, and for positive x, positive y. So we can actually get rid of 2 of the quadrants because there will be no values in them. Let's look at what happens when x tends to infinity. Well, cos squared gets divided by bigger and bigger values of x, so it should ideally tend to 0. Let's draw 1 over x to see what it's like. These sort of functions are in a kind of envelope, so when cos squared is 0, we will have zeros for our function, but when cos squared is 1, we will get points on the line 1 over x. Now, when we're near 0, that means we're dividing by a very small value of x, which means that 1 over x will be super huge. So we know we can't be on the line x is equal to 0, but it will be a vertical asymptote. And apart from that, we will just connect the dots that we already came up with. And there you have it. A regular cos squared that was between 0 and 1 is now squashed between 1 over x. Now that you've seen a couple of examples, try to come up with the function yourself. Don't make it easy because the interviewers certainly won't. Then try to plot it yourself using either the 9 points that I gave you or maybe the linear transformation that you can come up with yourself. Check it on Wolfram Alpha or MATLAB and repeat. Okay, so I've never done this kind of video before, but I really hope you enjoyed it, and the next time we'll be speaking about exciting Boolean algebra stuff. See you soon, bye!